Today, folks, what we want to do is we're going to do some activities that surround these kinematic formulas that we've been learning, okay? So the first activity, and I'm going to have you guys do this at home. All I'm really doing here is kind of giving you some idea how you might accomplish this. The first thing that I want to do is I want you to figure out what your own reaction time is. So you see something, your brain makes up its mind to do something, and then from the time your brain figures it out and sends signals to your muscles, how long does that take? Your reaction time. So if you have baseball players, for instance, having a rapid reaction time is very helpful. They got a pitch that's coming in at 100 miles an hour. They only have a split second to really decide to swing, for one, and then where to swing. So having a fast reaction time can be very useful. So you're going to need some help for this. And the one thing that you will need is you'll need a ruler. All right? You can use a ruler. You can use a yardstick if you want to, if you have one of those. If you don't have one of those around the house, even just get a piece of paper, fold it up so it's long like a ruler, and then you're going to end up dropping it. Okay? So if you don't have a ruler around the house, find a piece of paper or a stick that can drop straight down, and then you'll end up measuring the distance. Okay? You're also going to need a helper. Okay, so I've got a helper over here, and what he's going to do is he's going to hold this ruler so that the 0 is down here at the bottom. I'm going to hold my fingers so that the ruler can fall between my index finger and my thumb. And when I tell him to, I'm going to have him drop the ruler without warning me. So I'll just kind of give him a nod, and then when he wants to drop it, he can drop it. As soon as I see it start to drop, I want to pinch my fingers together and grab that ruler. So we will know how far it fell during the time that it took me to see it, my brain to process that it's moving, my brain to send signals down to my fingers and tell me to clamp down. Okay? That's how we're going to measure our reaction time. So we're going to do 3 trials, and then I'm going to come up close to the camera. Here we go. Whenever you're ready. All right, that was 9.5. I'm going to write that down. 9.5 centimeters, which would be 0.095 meters. Okay, we're going to do 3 trials, so we're going to do this again. Maybe I just got lucky. Ready when you are. You fooled me. Ooh, I was bad that time. 23, or 0.23 meters was my second trial. I don't know what I did on the first one. I got really lucky. I don't think I cheated. I'm ready when you are. He moved it. Yeah, we're going to have to do a 4th. You want to get 3 successful trials where you actually caught it. This one was 15 centimeters, or 0.15 meters. All right? So again, I want to bring this up close so you can see on a ruler what that really looks like. All right, you guys. So, oops. There it was. This is where my finger was. I had my fingers originally right at the bottom. And as it fell, I pinched my fingers together and I caught it so that the top of my finger was right at 15 centimeters. All right? So on a ruler, that's 15 centimeters. But remember that for every 1 centimeter, or I should say, there's 100 centimeters in 1 meter. So if I'm writing this in meters, which I rather would, I'm going to write this as 0.15 meters. All right? So whatever number of centimeters you have, just put the decimal point 2 places in. So 0.15 instead of 15. We want this in meters. Let's start talking a little bit about variables here. If we think about, we've been talking about these variables for a couple of days. If we think about those variables, what are they? I have 5 accelerated variables. They'd be a, vi, vf, delta t, and delta, in our case, it was falling down, so instead of delta x, I'm going to call that delta y, okay? Those are my 5 variables. Now, as that ruler fell, let's think about the variables that we know. All right, let's think about the variables that we know as this thing fell and I caught it. Do we know what A is? Acceleration. Remember that on Earth, which is where we are, we do have a constant. It is negative, I'm going to call it negative 9.8 meters per second squared, okay? Some of you guys, we may have been using 10, but this is the actual number. So we'll get a number closer, and you'll find out what your true reaction time is. How about VI? Did I know what the VI was the moment that the ruler was released? Well, it was released. It was dropped, essentially. It wasn't thrown, which means my VI is, of course, going to be 0. Okay? Did I know what the final velocity of the ruler was as it was falling and I caught it? I don't know how fast it was moving. So that's a big fat question mark. Do I know how long it fell for? No, I mean, we want reaction time. That's what we want to figure out. And so we have no idea how long it fell for. It was quick, but I don't really know what that number was. It's what I really, really want to know. Do I know what delta, remember, I got to have 3 of these 5 if I'm going to solve. Do I know what delta y is? I better, because I got to have 3. Well, that's what you measured on the ruler. So what I would do, I did 3 trials, and I expect you guys to do the same. I want you to write those 3 trials down on a piece of paper so that in the end, you're going to do a short video of you doing this. And then you're going to show me what your numbers were, okay? I had some really spread out numbers. What I would do is average them. Take 3 trials, average your 3 numbers. So add them together, divide by 3, okay? So I'm just going to say that when I averaged mine, I had some number. It's going to be probably right around 0.15, okay? So I basically have 3 variables here. Now you guys might remember in a previous video, because we got to start thinking about formulas now. The way I pick a formula to do this is I look for the one variable that I don't know, but I really don't care about. Okay? Now, these are the 2 variables that I don't know, but I really want the time. Time's what I want. That's what I'm trying to figure out here. So that means the variable that I don't know, but I really don't care about, that's VF. In your comps, you should have a formula that says no VF. All right? Now, if you look back there, the formula you should see, we'll call it delta y in this case, is that one. That's my no VF formula. We can simplify this. So if you're afraid of the math, don't worry so much. The fact that your VI was 0 means what about this formula? Well, if VI is 0 and it's multiplied by delta t, 0 times anything is going to eliminate. It's going to make it 0. And so this comes down to delta y equals 1/2 a delta t squared. Okay? Do I know what delta y is? I do. I know what a is. It's right there. The only thing I don't know, all right, the only thing I don't know is delta t. Now, some of you guys struggle with the algebra. I know that for a fact. If you don't struggle with the algebra and you're good with basically solving this for t, for delta t, you can go ahead and go do that. Okay, what I'm going to do right now is I'm going to do a little bit extra just to help you out with the algebra here. As time goes on, I'm going to wean you off of me, though, and you're going to have to start doing this on your own. Okay? But for right now, let's think about solving for delta t. If I want to solve for delta t, I want to isolate it first. So the first thing that I would do is I'm going to take and multiply both sides by 2. Okay, that's to get rid of the 1/2. And I want to get rid of the a too, so delta t is the only thing over here. But I'm multiplying the a times delta t, so I would need to divide it to get rid of it. Okay? So I'm going to clean this up right now. On this side, I would have 2 delta y, 2 times delta y divided by a equals, on this side, the half gets canceled by the 2. The a gets canceled by that other a because it's in the denominator and that's in the numerator. And all I'm left with is delta t squared. I don't want to know what delta t squared is. I want to know what delta t is. So the last thing I'll need to do, I'm going to take the square root of both sides. Okay? What that'll give me, I'm going to go ahead and flip-flop these. Here, delta t squared, if I take the square root of that, it's just delta t. Okay? Over on this side then, I'm going to have the square root of 2 times how far it fell, our delta y, divided by the acceleration, which is a. Okay? Do notice this, you guys. I said a was a negative 9.8 because gravity always goes downward. But also, our delta y was also falling downward, so that's negative also. Why would that be important? Well, if I plugged a positive in for delta y and a negative in for a, I'd have a negative square root, that doesn't exist. It's an imaginary number. All right, so this is the formula. You guys that might struggle with the algebra a little bit, that is the formula you want to use to do this. Let's talk about the second activity I would like you guys to do. And I've labeled this Be Isaac Newton. Channel your inner Isaac Newton. Isaac Newton is the one who figured out the way how that gravity worked. And so determining what gravitational acceleration was, this was all on Isaac Newton, and nobody had written these equations. He did it. So we want to see how could we figure out what gravitational acceleration is by experimenting, by testing, not by just trusting me that it's right around 10. Can we prove this out ourselves? So what I've done is I've written up an equation here. This equation is your no VF equation because VF is typically the hardest thing to determine. Measuring VF is really hard unless you have like a radar gun or something. It's very difficult to do in most lab situations. And so an equation like this that doesn't have VF in it, it's used a lot because it's such a pain to measure. So if I think about this equation, if I want to figure out Isaac Newton's gravitational acceleration, I would want to isolate this first. So I want to figure out what is gravity? What is gravitational acceleration? Well, if I do this, I'm going to isolate A. So again, I'm talking about the algebra right now. I would basically take this term and move it over here. That'd be the first thing that I would do. So I'm going to subtract VI delta t to the other side, and I would end up with delta y minus VI delta t. And that's going to equal 1/2 a delta t squared. Now, this should look kind of familiar. In just a minute, at least it will, because I want to think about, well, how can I prove how gravity is pulling something down? Well, I drop it. My experiment's going to be, I drop it. Your experiment's going to be, you drop it. Okay? If you think about it, I'll switch to my keys since my tape just rolled off the table. If I drop my keys, what's the initial velocity? Okay? The moment it leaves my hand, what is its initial velocity? Well, we've been over that. Our initial velocity here is going to be 0. Well, what does that mean about this term if VI is 0? If VI is 0, delta t, and at least in this term, it really doesn't matter. it goes away. And what I end up with is the same formula that we just looked at. Delta y equals 1/2 a delta t squared. Newton's genius wasn't in his ability to do math. Newton's genius was in his ability to visualize situations and apply math to them. This isn't that difficult of an equation, but he is the one who had to figure it out. So what we're doing here then to isolate A, because that's what we want to solve for this time, to calculate gravitational acceleration, the first thing I would do is I would multiply both sides by 2. Again, I want to get rid of the fractions. Fractions make me make mistakes. So I multiply by 2 to get rid of the 1/2. If I want to get rid of this delta t right here, so A is all by itself, because I'm multiplying the delta t squared times A, I would divide both sides by delta t squared. Okay? Just like that. If I clean this whole thing up so it's a little easier for you guys to work with, this cancels that. This cancels that. I'm left with A, which is what I want. What's on this side? I'm also flipping this, you guys. What is over here is 2 times delta y over delta t squared. That right there is an equation that will allow you to essentially be Isaac Newton. So what am I going to have to do? How am I going to get these numbers? I'm kind of working backwards here compared to the reaction time one. I started with getting what the distance was it fell before. Now I need to actually figure out how will I do this. Well, in part, I already talked to you guys about the fact that I have to drop something, because that's what allowed me to say this was 0 and kind of make this easier. So I know I'm going to be dropping it. What am I going to need to measure? Well, if you look at this, all I need is how far it fell. That's what your delta y is. And your delta t is how long did it take. So we're going to need these 2 variables. All right? How are you going to figure out how far it fell? Well, this is easy. I mean, you can use a measuring tape if you have one at home. If you have a yardstick at home, you can just put it against the wall and come it all the way up and then make a mark there and measure a little higher. I will tell you, the higher this is, the less the error is going to matter. There won't be much error here. You can measure very precisely how high up on a wall that you are. So you're going to measure that height. And then you're going to have to time it. Here's where the error is. I would use my stopwatch, your cell phone, right? Use your cell phone. You can have somebody time it for you and count it down, but I would go 1, 2, 3, drop. Start the timer at the same time that you drop it. Now, you're going to have to stop the timer when it hits the ground. That means it's going to be on and off, but the higher you can go, the less error that you're going to have with the time. Another good way to do this is you could, if you use 2 cell phones, you can have one with your timer on, just running, and you videotape that timer that's sitting on the ground running. You can videotape it with another camera, and then you can hear yourself say 3, 2, 1, drop. All right? So you'll hear in the video that countdown, and then you record the time when it started, when you do the playback on the video. When you heard drop, start the time, or look at what the timer says, and then when you see it hit the ground in the video, look and see what the timer says at that moment. That allows you to slow down the video. I'm sure you guys have done this when you sent videos to people. Now you're doing it for science. All right? So figure out what that time is, and it should not be long. It should be less than a second is more than likely what it'll be. That's where your error is going to be, and the more carefully that you do this timing, you guys might come up with a better method than I have. If you do, please share it. We'll use the heck out of it. But you're going to need how far it fell, so you're going to measure this, and then you're going to determine that time. And like I said, if you can manage to get a stopwatch on your cell phone running and catch that image with a second camera, so you can see what it's doing when you basically drop it, and then when you see it hit the floor, that's going to be the best way to get your times. All right? You got a formula. We talked about a plan. I want you guys to execute both of these and videotape yourself when you do it, at least one trial. I want to see how you guys do it. If you come up with a better way to get the time, throw it at me. I definitely would look at it and see whether it'll work for other things that we do. All right, you guys, so that's it. Get those two done. I'm curious to see how close you're going to get on this acceleration, and it all has to do with how careful you are in what you measure. But get this height that it falls from, measure that time, and that's going to be what we need.